All right, welcome back again. Chapter 3, Section 6.2, Euclidean domains. So this will be an even more special type of domain, and it'll be a stronger condition than being a PID. It's a common way to demonstrate something as a PID. All right, let's start with our definitions. All right, so first part of the definition, start with an integral domain D. And then we define a size function, which is just any old map from the non-zero elements of D into Z bigger than or equal to 0. And then there are different conventions on this, but the convention we'll use that makes things just simpler is we will always extend such a map to a map from all of D to Z bigger than or equal to 0, union the symbol minus infinity by sending 0 to minus infinity. All right, then we're going to define D and call it, we'll call D a Euclidean domain with respect to the size function sigma if it satisfies these two properties. All right, and here's the condition. It looks just like our division algorithm theorem, the conclusion of the division algorithm theorem for the integers. So Euclidean domains are domains in which something like the Euclidean algorithm holds. So given any A and B in the domain where B is not 0, you can essentially make sense of A divided by B written out multiplicatively. So there is a quotient Q and a remainder R, so that A is equal to BQ plus R, and the size of the remainder, sigma of R, is smaller than, strictly smaller than, the size of B. Now, over Z, we had a uniqueness condition, that there was a unique Q in R. That's not part of the definition of the Euclidean domain, just the existence. If you can do this, then you're a Euclidean domain. It doesn't matter if you can do it in lots of ways. All right, so let's do a couple examples, or at least mention them. Our first example is just the integers. We proved this theorem, and there the size function was just the value of n itself. We first proved it for the positive numbers, and then we didn't need the absolute value sign. And then the homework, or at least in the text, it's indicated it works for all integers, and you use this size function. All right, then we have another example. All right, the set of polynomials over a field, f of x. Here the size function is just the degree of the polynomial. And this was the type of long division you did with polynomials, I don't know, back in 7th grade or something, and you did long division of polynomials, and you were just demonstrating that it was a Euclidean domain where the size function was the degree. All right, here's another example. This is probably a new one for you. These are called the Gaussian integers, z attach I. And the size function here is just the modulus squared of this complex number, a squared plus b squared. I suppose it's not obvious that this is indeed a size function that generates a Euclidean domain. But since that's the whole content of the next section, I'll leave that for later. Anyway, here's another example of a Euclidean domain. And this is an example where the choice of Q and R is not always unique. I guess while I'm at it, I should say, let's do another one. Here's another one that I'm not going to do in detail, but it's in your homework. If you put two brackets around that x, f of double bracket x, those are called the formal power series. So they're just formal symbols where you instead of polynomials where you have finite sums, you have infinite sums, but you don't worry about convergence. There's no calculus here. So it's just a symbol where you have an infinite list of them, sum of ak, x to the k's. And if you grab off the first coefficient that's non-zero, then that degree where that first happens is the size function. Anyway, that's in the homework, and I'm not going to spend more time. Here's our first theorem, and I guess probably only theorem. Euclidean domains are principal ideal domains. And in particular, they're also unique factorization domains. Proof? Well, let's call D our Euclidean domain. Grab an ideal in there. We want to show that ideal is principal. This argument is actually essentially the same one that worked with Z. So here we go. All right, let's pick an A in our ideal I that's not 0. Of course, I guess we should say we're not looking at the 0 ideal because that's no work at all. So pick A in there that's not 0, and pick anyone with a minimal size. That always exists because the sizes are integer valued. So grab anyone in there, whatever that size is. If there's someone smaller, grab him. If there's someone smaller, grab him. But this can only repeated a finite number of times because there's only a finite number of integers below our initial choice and above 0. All right, now do the Euclidean algorithm. So we're going to take any element B and I, and we're going to do division by A on it. So that means you write B as AQ plus R with the size of the remainder smaller than A. All right, well, B is an I. A is an I is an ideal, so that product is an I. Move everything to the left side except for R, and we see that R is an I. Well, that's a bit of a problem here, because we chose A to be, of the non-zero things, to have minimal size in I. But if R is I and it's smaller than A, that would violate our choice of A unless the R was 0. All right, well, if R is 0, then B is just AQ, which means B is in the ideal generated by A, which means since B was arbitrary, everything in I is contained in A. But of course, A itself was an element of I, so A is contained in I, and altogether, that means I is A, so I is principal, and that's the end of the proof. All right, one final comment of sort of our hierarchy that we have so far. All right, first of all, we have all these conditions that are stronger on the left. Euclidean domains are always PIDs, which are always UFDs, which are always at least integral domains. Over on the integral domain, all we can really say is that prime elements are always irreducible, but we don't get the reverse. When we move up to UFDs, then prime becomes the same as irreducible, and we get some extra things like the ACCP condition holds and greatest common divisors exist and are unique up to multiples by units. When we move up to PIDs, we get that greatest common divisors not only exist, but they're linear combinations of what we are taking the GCD of. And we get prime ideals are maximal ideals. And when you move up to Euclidean domains, I don't know, I don't have anything to add here. Usually you start this chain by finding a size function. And then you get a Euclidean domain, but what you really wanted was everything to the right, the PID stuff. All right, that's it for the end of the section.